A small business network is often mistaken for a simple collection of computers plugged into a single switch, but in reality, establishing reliable communication requires active configuration and a specific design logic to prevent digital gridlock. In a commercial environment, small refers to the strict limits on your resources, your budget, available ports, and overall bandwidth. The engineering complexity remains identical to that of a global enterprise. This chart outlines the baseline components. You need a central router, a switch, and a wireless access point to act as the singular hub linking your wired and wireless users to a single internet connection. Without engineered predictability, this basic collection of hardware is a liability. You will run into routing bottlenecks, complex troubleshooting scenarios, and inevitable downtime. True network stability requires building from the physical layer up. You must take hard physical limitations and layer them with strict logical rules. A predictable system is the direct result of deliberate architectural choices that map those physical realities to logical policies. That mapping process starts at the foundational hardware layer. Choosing the right intermediary devices requires balancing four major factors. Port capacity and backplane speed directly drive your expenses. Network architects must anticipate future bandwidth needs today, like accommodating servers that will require 10 gigabit ports over standard 1 gigabit links. This introduces hardware expandability. You have to decide between fixed environments and those built to evolve. Fixed configuration devices have a hard limit on the number and types of ports they offer. Even the most expandable hardware is useless without the right operating system. The device's OS must natively support specific organizational requirements, specifically Layer 3 switching, network address translation, DHCP, and embedded security. Selecting the correct hardware combination upfront prevents you from having to rip out and replace your entire infrastructure during your next growth phase. The physical components dictate the absolute limits of the network. Poor selection immediately bottlenecks future scalability. Once your physical ports are established, you need logical identification. Assigning IP addresses in an ad hoc manner creates total administrative chaos for management and troubleshooting. To establish a predictable addressing schema, you use device-type block grouping. Specific pre-calculated subnets are reserved explicitly for infrastructure, like routers and switches, versus endpoints, like IP phones, printers, and workstations. This grouping strategy physically summarizes traffic identification. It makes it instantly obvious what type of device is transmitting data based entirely on its IP address. Let's look at a real-world execution of this policy to see how it absorbs network growth. Here we have a flow mapping a gateway, a switch, a server, and a PC. Notice that the switch is assigned the address 192.168.2.5. That value falls perfectly within the predefined subnet boundary for switches. If a second switch is added at .6, it remains under that exact same summarized /30 boundary. Because it stays within that boundary, the core router requires zero policy rewrites or security rule updates to accept the new hardware. The entire network natively trusts the address. Deliberate planning along subnet boundaries separates an amateur setup from an enterprise-grade design. Logical schemas act as the connective tissue. They transform a random collection of MAC addresses into a structured, easily auditable system. Even the best logical map cannot prevent a physical hardware or link failure. In a single link network, one failed router halts all business continuity. The engineering solution to a single point of failure is redundancy. By introducing duplicate equipment and crisscrossing links, you create alternate pathways. If the primary path through router 1 fails, traffic automatically reroutes through router 2 without dropping the connection. This capability is defined as high availability and fault tolerance. Reliability comes from the geometry of the design. By overlapping backups, engineers ensure the network functions regardless of individual component health. With the physical path secured, the focus shifts to the data itself. Different types of traffic require specific handling based on their sensitivity to delays. Real-time traffic, like voice and video, will drop out if it is forced to wait in the same processing queue as bulk email or file transfers. Routers and switches use quality of service, or QoS, to classify and prioritize traffic during congestion. VoIP calls require a high priority tag, so they are sent to the backbone first. Standard applications like instant messaging receive best effort treatment with no guarantee of priority delivery. Maintaining these QoS rules and addressing schemas requires persistent administrative oversight. Most of this work happens through remote terminal sessions with the device's operating system. Remote administrative sessions grant full control over the network, representing a massive security risk. Unencrypted protocols like Telnet expose credentials to anyone. Secure Shell, or SSH, is the mandatory standard, encrypting all traffic to protect your data while interacting with the router's OS. A fully functional network actively triages its internal traffic while simultaneously defending its administrative pathways from outside compromise. With the physical, logical, and application layers built, the network must be continuously monitored to anticipate future scale. Scaling effectively requires analyzing exactly what protocols and services are consuming your network resources. Protocol analyzers and built-in OS tools reveal the truth about application behavior and CPU utilization. This specific data guides your budget and expansion decisions. Before scaling, you must prove logical routing works. The fastest way to verify Layer 3 connectivity is the ping command. It tests connections by sending an ICMP Type 8 echo request, then measures the round-trip time to receive a Type 0 echo reply. A successful ping sequence with 0% packet loss proves that the addressing schema, physical links, and routing tables are properly aligned. Engineering a small network involves applying enterprise principles to a limited physical space. Success means guaranteeing predictability, security, and scale through meticulous design.